Okay, so the next lesson we have here is on integrated rate laws. Integrated rate laws are going to represent how the concentration changes as we let the reaction progress. So we're going to measure time, and we're going to measure the concentration of the reactant at specific points within that time period. And we can look at how the concentration of the reactant or reactants will change with that time. It will allow us to do a couple of things, like, for example, what's listed down here at the very bottom is to determine how long it takes to get to a very specific concentration. But it will also allow us to know information like how long do we need to let this sit before we can dispose of it properly. And so integrated rate laws are a much more valuable tool for us in some cases. Not in every case, but in some cases, this is much more valuable for us because it allows us to do some more complex concentrations. However, because it allows us to do these more complex concentrations, it does require, in some cases, that we use calculus, because most of the time when we're graphing these concentrations, we will see that there is a curve on our graph. And the curve, in order to determine the slope of the curve, we need to use calculus, and that is generally a skill that's lacking in high school. So it makes it a little bit more complicated, but we can graph a variation in order for us to see see what the reaction order is. The concentrations of these things can be measured in a variety of ways. Sometimes it's done with color, sometimes it's done with pH. It really just depends on the substance. So in order to determine the reaction order, we can make a series of graphs, and we're going to talk about first order, second order, and zero order integrated rate laws. And I will tell you on each of the next couple of slides which graph we need to make in order to determine, or what those graphs look like in order to determine what the reaction orders are. So I guess let's go ahead and get started with the first graph. So we have first order reaction listed here, and our integrated rate law is going to take on the form of the equation: the rate equals K, which is our rate constant, times the concentration of A. The rate of reaction is going to be determined by the disappearance of A, because again, this is our reactant, and as this starts to disappear, we're going to see that the concentration, as this disappears, the concentration will drop, of course. But we're going to see that the reaction can slow down, because if there's less and less of that material in there, then there's less interaction. So when we are looking at our first order integrated rate law, we are going to use the equation for our graph is going to be the concentration of A equals the initial concentration of A. That's what that A in brackets with the 0 subscript is. That's the initial concentration. And we're going to multiply by E raised to the negative KT. And so K is going to be our rate constant, and T is going to be the time that the reaction has proceeded. In order to really understand this equation, in order to really be able to use this equation, we're going to get rid of E. That's hard for us to work with. And so if we take the natural log of both sides, we get this form of the equation. And so the natural log of the concentration of A is equal to negative KT plus the natural log of the initial concentration of A. The E in our equation here dictates that we have to use the natural log. If this was a 10, we would use just the regular old logarithm. But because this is an E, we have to use the natural log in order to eliminate that exponent and eliminate the E. So the average rate of reaction, I'm sorry, let me back up for just a second. So the integrated rate law would be this one right here. And we can actually look at this and graph it. This is a linear equation. So you don't have anything that's raised to an exponent. So in order for a reaction to be a in order for a reaction to be a first order reaction, we would graph the natural log of A versus time. if this graph gives us a line, then that is the reaction order for A. If it does not give us a line, then our reaction is not first order in A. And when we say the natural log of A versus time, we always read it as this is on the vertical axis versus this is on the horizontal axis. And so if this gives us a line, then we know that the reaction is first order in the concentration of A. Again, this requires some calculus magic that I'm not going to go into because I don't believe you guys are doing, well, you're probably doing differentials right now, but we're not going to get into that. So we're looking at the change in the concentration, and then we're looking at how the concentration of A changes over time. And so if this gives us a line, then it's first order in the concentration of A. So let's move on to the second order equation. So the rate equation would look like this. We'd have rate equals our rate constant times the concentration of A squared. And then through some other magic, some calculus magic, I've just given you the integrated rate law here. We've got 1 over the concentration of A at some time, which is the same thing that we would have here, it's just at some time, equals our rate constant times the time plus 1 over our initial concentration of A. So if this gives us, again, this is a linear equation, right? And if this gives us, if we would graph 1 over the concentration of A, this is not the initial, versus time, again, excuse me, versus time, then if that gives us a line, then we know that the reaction is second order in the concentration of A. So if we graph this first relationship and get a line, it's first order in the concentration of A. If we graph the second relationship and get a line, it's second order in the concentration of A. And so that's going to allow us to really narrow down the reaction order. You will not get you will not get a linear relationship for both of these. It's going to be one or the other. This is when we have the reaction only varying in the concentration of A. However, if we would have multiple substances, then we would need to look at a different form of this equation. We would look at, if we had the reaction, if we had the rate law, R equals K, the concentration of A times the concentration of B, which would also be a second order reaction, right? They're first order in both of those. So together the overall reaction is second order, then we would have to graph, oh, I'm sorry, this is the natural log of, no, that's correct. We would have to graph the concentration of A over the concentration of B to see, it'd be this, it'd be the natural log of the concentration of A over the concentration of B versus time, and that would give us, if that gives us a line, then we know that that is second order in a second order reaction, integrated rate law. Sorry. So then the last one we're going to look at is zeroth order. Zeroth order looks like this. We have the rate law. Rate equals our rate constant times the concentration of A raised to the 0 power. Anything raised to the 0 power is 1, so it's really just the rate equals our rate constant. In this reaction, the rate is going to be independent of the concentration of any substance. And so this would be the form of our integrated rate law, because the concentration of A is equal to negative kT plus the initial concentration of A. The concentration is not going to affect the rate. So this rate law, these two would divide out to 1, and so they're gone. This reaction will occur independent of the concentration of A. It doesn't matter what its concentration is. And so in order to determine if it is zeroth order, we would graph the concentration of A versus time. And if we get a line, then we know that it is 0th order in the concentration of A. So this one is for first order, this one is for second order, and this one is for 0th order. And we graph all three of these when we are looking for an integrated rate law. Whichever one gives us a line is the one that tells us the order of the reaction. And so that's kind of the standard practice. We will graph those three things when we're looking for to determine the order of our reaction. So I want to move on to half-life, because if we look at half-lives, generally when we talk about half-lives, we're thinking about radioactive substances, but we can talk about the half-life of these reactions because it is really how much time is required for the reactant to decrease by half. And so the half-life still applies to both of these. We can find what that half-life is, but it does depend on what order the reaction is. And so if the reaction, these are typically because of decomposition reactions. I want to make sure I say that. Half-lives are typically decomposition reactions. They don't have to necessarily be, but they typically are. So that is, let's see. Here's how we can determine the half-life. T with the little 1/2 subscript, that is the half-life. And for first order reactions, we're going to take 0.693 divided by K. That tells us that first order reactions are independent of reactant concentrations. It doesn't matter what they are, it's going to be that value regardless. Second order half-life reactions can be found by using the half-life is equal to 1/K times the initial concentration of A. And then for our 0th order, half-life is going to be the initial concentration of A divided by 2K, which is our rate constant. And if we calculate these, depending on what the reaction order is, if we calculate the appropriate half-life, then we know how much time it's going to take in order for the reaction to decrease, the reactant concentration to decrease by half. So those rate laws, like I said, they're more complex, and I don't want to go into all the details. If you're really interested, then I have them. I have some of that math worked out in my notes, but I don't want to get into that. I want you to be able to use that. So if we're trying to determine the reaction order for an integrated rate law, we're going to make these three graphs, and whichever one gives us a line will tell us the reaction order. Then once we know the reaction order, we can calculate the half-life, which will be how much time has passed in order for half of that reactant to be gone. So that brings us to collision theory, which in one of the other videos I promised you, actually the second video I promised you we would get into. And so we're going to talk a little bit about collision theory and what that represents, because this is how reactions are occurring. I mean, we don't really think about it on an atomic or molecular level when we're writing reactions, but this is how reactions occur. This is what's happening in a beaker. This is what's happening in your body. So for collision theory, the rate of reaction is proportional to the rate of reactant collisions. In order for these reactions to proceed, the reactants have to be in contact or have to come close to each other. And so they are constantly moving around. That's just the nature of matter. But as they run into each other, if they run into each other in the right orientation and with the right amount of energy, then they can join together. And that will allow the reaction to occur. So the second step here, or the second point here, is the reacting species must collide in an orientation that allows contact between atoms that will become bonded together in the product. And so the reactants can't run into each other in any orientation just to become reacted. They have to run into each other in the right orientation. So if they run into each other in the right orientation, then they can connect with each other. However, if they run into each other in the wrong orientation, there's no way to connect. And so that reaction, they'll just bounce away and they'll wait until they hit each other in the right orientation in order to really react. And so if these concentrations of our reactants are decreasing, then you're not going to get a high collision rate. And if there's no high collision rate, then the reaction is going to slow. Or if there's a low collision rate, then the reaction will slow. And as we decrease our amount of reactants and we put other stuff in there, whatever our products are, then you're going to get collisions between products and reactants, between products and products, and between reactant and reactant. And so the amount of reactant collisions will decrease as time proceeds for these reactions. And then number 3, the collisions must occur with adequate energy to permit mutual penetration of the reacting species' valence shells so that the electrons can rearrange and form new bonds. And so if they just come in with very little energy and they kind of bounce off of each other, you don't have enough energy for those repelling electrons to allow their valence shells to overlap enough so that the electrons can be rearranged to form those new bonds in these products. And so sometimes that's why sometimes we have to heat reactions up in order to get them to react. Sometimes we have to cool them down so that they are back in that window of allowable energy. And so sometimes they are hitting each other with so much energy that instead of giving a chance for those electrons to react, they just bounce right off of each other and move in opposite directions. So it has to have the right amount of energy, it has to be in the right orientation, and that's going to be proportional. The rate of reaction is proportional to our collisions because they have to interact before they can react. That is collision theory. So during this collision between these particles, you end up with an activated complex or something called a transition state. And so it just depends on the text that you're reading or interacting with what it's called. But it gives you this weird molecule that is part of your reactant, but also kind of looks like your product, where they're kind of all interacting in the same region. It's a very, very high energy state, and it assumes that the reactants have come together with the proper orientation and adequate energy, and you can form this activated complex. We know it's an activated complex because of this weird double plus sign that we have up here that indicates that is not a part of the reaction that we would write for this process. It is unstable, incredibly unstable, and that's good for us because once it forms, it's going to break apart right away, and we just hope that it breaks apart in a product and not another reactant. It is an intermediate state, and so we don't see this in our chemical reactions. This is just something that's kind of forming. It's a complex that forms, and then after it forms, something's going to break off or something's going to rearrange, and you get a product or you get a reactant back. It is very short-lived because it is so unstable, and there is an enormous amount of variation in what these activated complex and transition states look like for even just the same reaction, because they have to come together in the proper orientation, and they have to come together with adequate energy. And so you do get some funky things going on when you have varying polarities. You get some funky things going on when you have very complex structures. What we have here is a pretty simplistic structure. We don't know if the hydroxide is coming in or leaving. We don't know if the chloride is coming in or leaving, but you can see that the carbon with the 3 hydrogen on it are in a trigonal planar orientation, and so you've got space on both sides for those other 2 things to be, and so one is going to come in from one side and kick out the other thing. And so that is going to be somewhat like a tug of war. Sometimes the hydroxide wins, sometimes the chloride wins, and you end up with one product or one reactant back. And so it really just depends on what's happening. It just depends on what happens. It's very unstable, it's very short-lived, and there's a lot of variation. And again, to throw this back to what we did in anatomy, we talked about proteins that fold and having to have those right orientations for things to be able to come in and interact. This is the kind of thing that's going to happen when you have an active site in a protein. You have to, if it's not folded properly, then you won't be able to get that. You won't be able to get these things to move in here and act the way that they're supposed to act. The carbon is in the trigonal planar orientation, and so you get total access to that carbon on the sides here because the hydrogen is up and the 2 hydrogen are down, they're all in the same plane. And so the sides are open for the carbon to take on or react in this way. This notched arrow here, that's indicating that the hydrogen is coming out of the plane of the board. And this dark one, I'm sorry, the notched one is going behind the plane of the board. The dark one is coming out of the plane of the board, but they're all aligned in this direction. And so you've got those 2 sides open for the reaction to occur. So what happens then is you end up with, and this I hope looks familiar from anatomy, you end up with these graphs that indicate an activation energy. So this is the amount of energy that is required to form a product when you have reactants colliding with each other. And at the peak of both of these graphs, this is where you would have that activated complex / transition state exist. And it's going to take a certain amount of energy to get to that point. And we can add that energy in several different ways. Temperature is probably the easiest way to handle that. If we increase the temperature in some cases, we can get up to that high energy state. But what can happen then once you're at this high energy state, and this is true of both graphs, the activated complex or transition state, if the bond that we want to form a product forms, then we kind of fall down this way and we're at a lower energy or a higher energy, depending on the type of reaction we have. And if it falls back down this way, then we end up with a reactant again. And so no harm, no foul, because there are other things in there for it to collide with in order for that activated complex or transition state to form again. And then you can have a product form. And this process is just going to continue until either we stop it or we run out of a reactant. But this specifically shows us endothermic versus exothermic reactions. So endothermic means we have to put energy in order to get our products. And so we put energy in because the amount of energy that the reactants have at the beginning is lower than the amount of energy that the products have at the end. And so the difference here is the energy that was absorbed by these products or by these materials to form the products. For an exothermic reaction, energy is given off, and so after the products are formed, they are much lower in energy than the reactants, and this amount of energy had to be given off. This is similar to what we talked about with electron transitions when we were talking about quantum mechanics and giving off photons of light to form our atomic emission spectra. In order for the products to form, in this case, they have to be lower in energy, so that lower in energy means it has to lose a certain amount of energy, it has to lose that much energy, and that much energy is given off in terms of heat, right? Exothermic, out heat. In terms of endothermic reactions, to get the products to form, we have to put energy in. We have to put in this much energy, and endothermic means in heat. So we have to put in that much heat, not in heat like biologically, but we have to add heat to this reaction in order to get our products to form, because the products can't form without having that additional energy added. So when the activation energy is larger than the kinetic energy of the particles, then we have a very slow reaction that will proceed. When the activation energy is smaller than the kinetic energy of the particles, then the rate will be much faster, and that's generally why we heat things up when we are trying to get a reaction to go faster. That doesn't always work though. Sometimes we have to cool it down in order for the energy to be at the right spot for the reaction to go faster. It really just depends. So we're going to move on to the Arrhenius equation. Oh, I should say really quickly that the activation energy is temperature dependent. And so we also have the rate constant that is temperature dependent. And so that leads me into the next slide, the Arrhenius equation. This is going to relate the activation energy and the rate constant. It shows us the relationship between the two. And so we have the expression here. We've got our rate constant is equal to A times E raised to the negative EA, that's our activation energy, divided by RT, excuse me. So K, our rate constant, is equal to A, which is called a frequency factor, and it has to do with the number of collisions that are occurring. it's got units. So the units of A are going to be liters per mole second. Those are the units of A. And again, that's going to give us an indication of how often we're getting collisions with the right orientation to form the activated complex or transition state. Okay, so that's A. That's our frequency factor. And then we've got E, which is the number E, raised to the negative E subscript A. That's our activation energy divided by R, which is the ideal gas law constant. And the one that we're going to use is the 8.314 joules per mole K. And then we've got T. T is our temperature in Kelvin. And I should say that our activation energies have to be in joules per mole. And so if that is the case, then everything will work out to give us the proper units for what we want. So the Arrhenius equation is going to allow us to compare two different temperatures. And you can see the expression here. We took the negative log of this in order to eliminate E. And so then we took two different temperatures and looked at the comparison of those two different temperatures to get this expression down here. And so this equation is going to compare the rate constants for two different temperatures. The activation energy for both of those are going to be equal to each other. The activation energy is generally equal for a reaction. It's constant for a reaction. But when we're comparing the two temperatures, the rate constants and the two temperatures will be our variables that we're comparing. I said that the activation energy is temperature dependent. It is temperature dependent, and so we're going to hold it constant for this relationship. I do want to point out, though, that once we took the natural log of this entire equation here to get this form of it, we can graph this, and we get y equals mx plus b. So we have another equation that is linear that we could graph and look at the relationship. We'll do that on the example coming up. So, okay. So let's do that example. It says to graphically determine the rate of decomposition of hydrogen iodide using the following experimental data. So I can take this experimental data and I can plug it into my equation. And once I do that, I can graph the natural log of K versus 1 over temperature. And so what I'm going to do, I'm going to take the natural log of my rate constant, I'm going to take 1 over the temperature, and I'm going to just make a new table, or make 2 new columns in this table, and I'm going to graph this relationship. That's what it showed us in that last equation, or that last slide, where I showed you it was y equals mx plus b. And what we get from this data is a line that looks like this. The y-intercept down here is going to be equal to negative 12.6. And the slope of this line is going to be 5.09. So the natural log of K equals negative EA over R times 1 over T plus the natural log of A. And so our y-intercept is going to be this negative 12.6. That's going to be the natural log of A. That's going to tell us something about the frequency of the collisions with the right orientation. And the slope of this line is 5.09. And that's going to tell us about the activation energy divided by the rate constant. That's all I have worked out in my notes. So, negative 12.6. Okay. I have another example here. Determine the rate of decomposition of HI at 600 degrees Celsius. So, this goes with the last slide. We're going to determine the rate of decomposition at 600 degrees Celsius. We're going to use the natural log of K equals negative EA over R 1 over T plus the natural log of A. And so now we can plug the information that we found from our graph into this, and we can find our rate constant. So I'm going to ask you to pause the video and see if you can solve for K. And I'm going to go ahead and plug this information into my equation now. So we graphically determined it from experimental data what our slope and our y-intercept were, so that we can now do this problem where we're trying to find the rate of decomposition at 600 degrees Celsius. And so now I'm going to go ahead and just plug this information in. I'm looking for K. Negative EA over R is still going to be 5.09, and then 1 over my temperature, but my temperature has to be in Kelvin. So 600 degrees Celsius in Kelvin is 873. Then I'm going to add on to this my negative 12.6. And when I do the math, I get the natural log of K is equal to negative 12.6. Seems weird. And so in order to find K, I have to undo the natural log, I have to take E. So the inverse of a natural log is to raise E to that power. So I'm going to take E to the natural log of K equals E to the negative 12.6. And that simplifies down to K equals E to the negative 12.6, which E is a number. So a number raised to another number is going to give us just a number. And so if I type this into the calculator, E raised to the negative 12.6, I got 3.37 times 10 to the negative 6. 3.37 times 10 to the negative 6. And the units on this are going to be liters per mole seconds. But I recognize moles over liters as molarity. So this is really 3.37 times 10 to the negative 6, molar to the negative 1, second to the negative 1. Because moles per liter is flipped, so that means that molarity is on the bottom. So 1 over molarity times seconds is molarity to the negative first power times seconds to the negative first power. So we had to graphically do this to determine our y-intercept and our slope, so that when we were ready to find the rate, we could find, we had all the information we needed to do that at a specific temperature. So I hope you got the same thing that I did. Working with natural logs or logarithms can be a little tricky. Let's move on because we've got just a little bit more to go over. So sometimes we can have what's referred to as the rate limiting step in a reaction. And so what I have here is this is called a reaction progression graph. And we've got multiple activation energies that have to be met here in order to form several different transition states. And so this is going to be some of our more complex reactions that occur. These are the kinds of things that are happening inside of the body. You have lots of complex things that are happening, and these are taking multiple transition states. And so in order to get to our final product, this has to go through 2 transition states on this graph. And the transition state 1 and transition state 2 are at different activation energies. And so this specifically is for multi-step reactions, and we're looking for the slowest step. And the slowest step is going to have the highest activation energy. And so this one is going to be a lot easier to overcome that activation energy than it is to get here, because they get stuck in this kind of little valley here because of that peak is so high. And so it is the slowest step. The activation energy is the highest. But once you get over that activation energy, then your products are lower in energy than what your original reactants were. And we don't see either of these transition states in our final chemical equations. However, you can end up with contaminants in your products if you cannot get these things all over that second hump. So you have to make sure that you can get them all over here so that you have a nice, clean, pure product at the end. But this one would be our rate limiting step, or rate determining step. That's what RDS stands for, rate determining step. Where'd my mouse go? Okay. The rate limiting step must determine the rate law for each step. In order to write the rate law for this, we have to determine the rate law for each part of the process. So you're going to have multiple rate laws to describe each transition state, and they will not be listed overall in the final overall rate law expressions. We cannot list transition states. They don't exist for any period of time. They're unstable, and so they do not determine the overall rate of the reaction, but the rate determining step will, the rate limiting step will. It will determine the final rate law for the reaction. And then I have a slide here about catalysts, and again, we talked a little bit about these in anatomy, but catalysts we use catalysts in chemistry as well. Palladium is a catalyst that likes to suck hydrogen in, and so it holds on to hydrogen in order for reactions to occur when you need hydrogen to be in one location. But catalysts, they will speed the rate of reaction by lowering the activation energy. And so what happens is, without a catalyst, you have this green activation energy, and with a catalyst, the activation state is much lower. You have the purple line. And so when you have a catalyzed reaction, you lower the activation energy, and it allows the reaction to proceed at a much faster rate without a lot of interaction. These do not change that balance between the reactants and the products. All it does is it allows the reaction to proceed more quickly. The catalyst is not consumed during the reaction. They are regenerated. And what I mean by that is that they are, we can recover them from this reaction and use them over and over again. They do not get altered at all. Generally, what catalysts do is that they'll grab onto this reactant, and just bring them close to each other so that they can react with each other. And then once they reacted, then lets it go, and then kind of just goes, and it keeps doing that. So a catalyst can cause the reaction to proceed at a much faster rate. And that is all I have for this set of slides. This is the point where you can view the 4th video.